our first talk is a split merge talk. So there will be 2 speakers and for each papers, and each speaker will speak about 15 minutes and then handle the question and then turn to the next talk. So the first talk, which is titled Two-Way Assisted Capacity for Quantum and Private Communication, will be given by Riccardo. Let's welcome him. Thank you.
Okay, thank you. Good afternoon to everybody. So let me first say that it's a great pleasure to be here at my first QIP and to have the opportunity to talk to you about some recent development on two-way assisted capacity for quantum and private communication. This talk is based on this paper here, which is a joint work with other people at the University of York, in particular Stefano Pirandola, my PhD supervisor, Carlo Ottaviani, and Leonardo Banchi at the UCL in London. So let me start from a very basic question, that is, if we consider an arbitrary task that can be implemented over a quantum channel, which can be, for example, the transmission of qubits, entanglement distribution, or quantum key distribution, we ask what are the optimal rates that can be achieved by point-to-point protocols designed for this task. So these are the two-way capacities of the channel, which are defined usually after optimization over adaptive local operation and classical communication. This means local operation assisted by two-way forward and feedback unlimited classical communication. So we consider the most general adaptive protocol that can be implemented over a quantum channel for an arbitrary task and for system with arbitrary dimension. Okay, so let's see how this adaptive protocol works. We have Alice and Bob. They start with 2 local registers, A and B, that basically are 2 ensembles of a quantum system. They first apply a round of LOCC in order to prepare the initial state of the protocol. Then we have the first transmission. Alice picks one system from her ensemble and sends it through the channel. Bob receives the output, and then they run a second adaptive round of LOCC, where the local registers are updated. Then we have the second transmission through the channel, and so on, another round of adaptive local operation and classical communication, so on for n transmission over the channel. So what do we have at the output of this protocol? We have an output state shared by Alice and Bob, which clearly depends on the sequence of adaptive local operation and classical communication that here is indicated with the letter L. We have this output state, rho A and B, and we say that the protocol has a rate R if this output state is close enough to a target state, phi n, that is characterized by R bits per use. Then, by taking the asymptotic limit in the number of channel uses and optimizing over the adaptive protocols, we define the generic two-way capacity of the channel. Clearly, this is a general definition. We need to give it an operational meaning, so we need to specify the task. This means to specify the target state of the protocol. So, for example, if the target bits are quantum bits, the two-way capacity is the two-way assisted quantum capacity of the channel. Whereas if the target bits are secret bits, Alice and Bob are implementing quantum key distribution, the two-way capacity is the secret key capacity of the channel. Okay, let me say at this point that these rates are optimal point-to-point rates. We are not imposing any restriction, any constraints on the LOCC, any restriction on the number of channel uses, and no restriction on the input energy of the protocol. So in this case, we are giving implicitly benchmarks for quantum repeaters. So, okay, having defined these two-way capacities, we need an upper bound to them, and this is the main part of this talk. We design a reduction strategy in order to compute this upper bound. And this strategy is given by the combination of three ingredients. The first one is the notion of the relative entropy of entanglement extended from quantum states to quantum channel. The second ingredient is the LOCC simulation of the quantum channel. And the third ingredient is the teleportation stretching of the adaptive protocols. Thanks to this strategy, we are able to upper bound the capacity, the two-way capacities of the channel with a quantity which is a single letter quantity, which is, and so in principle computable. So, okay, let me start by the first ingredient, the relative entropy of entanglement for the quantum channel, which is defined in this way in terms of the relative entropy of entanglement of the output state. We say this as a theorem, and we give three alternative proofs for this upper bound, depending on different technical assumptions that we can make on the size of the shield system that, together with the key system, define the private state, the target state. So the first proof, in the first proof, we assume that the size of the shield system grows at most exponentially in the number of channel uses, and this is justified by this by an argument that can be found in this Cristandal paper in 2012. So we are able to write down a finite type inequality in this way, with a term that depends on the dimensionality of the target state, that with this assumption can be shown to grow at most exponentially. The second proof, in the second proof, we assume that the energy of the output state and the target state grow at most exponentially, whereas in the third proof, we do not give any assumption in the size of the shield system, and we write a finite type inequality to upper bound the rate of the protocol in this way. Now we have a term that depends only on the dimension of the key system. So, okay, we have our upper bound, but as you can see, this is too difficult to compute due to optimization over LOCC, which contains feedback, and also due to the asymptotic limit. So we need a strategy to simplify this, basically this output state, which means simplify the adaptive protocol. So this simplification is brought by first by the LOCC simulation of the quantum channel. So any quantum channel can be simulated in this way. What is the LOCC simulation? Basically, is you can think of a generalization of the teleportation LOCC protocol. So we have this situation here. Alice has an input state rho and shares with Bob bipartite state sigma. She makes some measurement on her local system and communicates classically the outcome to Bob, which in turn apply some other measurement on his local system. Then, by averaging over all the possible outcome, he obtains a state which is not rho, of course, but contains some noise. So this can be seen as the output of a noisy channel. And we can write this output as the action of the LOCC over the input, over the tensor product of the input state and the resource state sigma. Okay, we have also, let me say that we have this idea of LOCC simulation have a precursory we can find precursory idea of a DSL-OCC simulation in this paper, for example, by Bennett, where the simulation was made through teleportation, but was restricted just to Pauli channel. But also in this paper by Nielsen and Chuang, we have a simulation through joint quantum operation restricted to programmable channel. So, okay, now we have this LOCC simulation of the channel. We can consider a single instance of the adaptive protocol. then we can substitute the transmission over the channel with its simulation over the resource state sigma in this way. So we have now, there's no more the channel, but we have sigma and the local operation on Alice and Bob's side. We can stretch back in time the resource state out of the adaptive protocol, and by iteratively doing this for all the n uses, we obtain the reduction that we achieved the reduction that we needed. So we can basically write the output of the protocol in this way, where all the adaptive LOCC are collapsed into a single final round of LOCC lambda bar applied to n copies of the sigma of the resource state sigma. Okay, this procedure is very general. In this reduction procedure, we have maintained the task. So a QKD adaptive protocol is translated into a block QKD protocol. It can be applied to any channel and for system of arbitrary dimension. So now we come back to our upper bound. We can substitute this new expression for the output state that we found, and we can exploit some very nice property of the relative entropy in order to simplify this upper bound. So we can get rid of the optimization and the asymptotic limit. So we have an upper bound which is a function of a single letter quantity, namely the relative entropy of entanglement of the resource state. But we can do even better. We can do even better if the channel suitably commutes with the teleportation unitaries. The channel can be simulated through teleportation. So this means that the resource state can be chosen to be the Choi matrix of the channel. So for this Choi stretchable channel, we have this upper bound now, in terms of the relative entropy of entanglement compute over the Choi matrix of the channel. So let me give you some classification. We have that the Choi stretchable channels are represented by a wide class of channels, namely the bosonic Gaussian, all the bosonic Gaussian channels and the Pauli channels. But we have also a subclass of these Choi stretchable channels that are represented by what we call distillable channels. And for these channels, we have that the upper bound in terms of the relative entropy of entanglement coincides with the lower bound given by the one-way distillability of the channel. So for this kind of channels, we exactly compute the two-way assisted capacity of the two-way assisted capacity. So okay, let me give you some very simple expression. For example, for the lossy channel with transmissivity eta, we have the Q2 that is equal to the secret key capacity, and is minus log 1 minus eta. And here you can see also the two-way capacities of the other distillable channels. And let me stress the fact that before our work, only the two-way quantum capacity of the erasure channel was known. So if we consider also the lossy channel, we can expand this expression here for long distances, which means high losses, and we can give the fundamental rate loss scaling of any repeaterless quantum communication. We have this scaling here, which is 1.44 eta bits per use, and we can plot it as a function of the distance between Alice and Bob, and compare it with all known QKD protocols in both discrete and continuous variable. And as you can see, ideal implementation of CV QKD protocol are not so far away from our fundamental rate loss scaling. So, okay, let me conclude. We have designed a strategy to compute the upper bound. This strategy is given by the combination of several ingredients, the channel's relative entropy of entanglement and the teleportation stretching. And thanks to this, we are able to give an upper bound in terms of a single letter quantity. We compute exactly the two-way capacities of many channels, the lossy, the amplifier, the dephasing, and the erasure. And we give also the fundamental rate loss scaling for any optical quantum communication. and benchmarks for quantum repeaters. We have some, also some recent developments of our technique. For example, it's been extended to a chain of repeaters and networks, but also to a more complex situation where multiple users are considered. But it has also extended to quantum parameter estimation and channel discrimination. But also we have, it has been proved that our bounds are also strong converse bound in this very nice work. But this is the topic of the next talk by Mark. So I can stop here. Thank you for your attention.
Do you want to set up? Okay. Do we have any questions?
Hi, can you explain a little more the detail of how when the teleportation step does not have trivial syndrome, how the correction can happen when you use this stretching method with the state sigma?
Sorry, say it again?
So when your channel is not covariant,
yeah.
and your teleportation method is not having trivial syndrome, how do you actually get the channel to work correctly?
Yeah, well, I don't know, in the sense that you can always simulate the channel with a resource state sigma and some LOCC, but it's very hard to find this the resource state in the case when the channel is not covariant. But the stretching technique, you can apply the stretching technique in any way. So the stretching technique is general, and it works also for non-telecovariant channels. Yeah, for amplitude damping channels, there is some way in the sense that you can suitably decompose the amplitude damping channel in three parts, and you notice that the central part is the part that is choice stretchable, so you can discard the two other parts, and you can choice stretch this single part, but the bound that you obtain is not so tight, it's not so good, and in the case of the amplitude damping channel, the squash entanglement works better and better than the relative entropy of entanglement.
Okay, due to the time constraint, let's just thank you, the speaker, again, and let's welcome the next speaker. So the next speaker will be by Mark Wilde, and he will talk about converse bound for private communication and over quantum channels.
Okay, thanks for sticking around for the last few moments of QIP. Let me bring up my talk. Okay. Okay, so, excuse me. This is joint with Mario Berta, who I think had the most accepted talks at QIP but did not show up. He's covering for Fernando to teach at Caltech. And Marco Tom-Michel, a joint collaborator who's somehow in the middle of a transition between University of Sydney and University of Technology, Sydney. Well, okay. Thank you. Okay, so the picture is very similar to what Riccardo discussed in the previous talk. We're interested in very similar things. This is the picture that I'm drawing. I guess the laser doesn't work. Anyway, so we're allowed little n uses of a channel connecting Alice and Bob, and they're allowed to use local operations in classical communication between every channel use. And we're interested in the maximum rate at which they can produce secret key. That's the goal at the end of the protocol. The eavesdropper gets the purification of each channel, the environments of each channel, excuse me, and is allowed to listen to all the classical communication that takes place. And this is some kind of toy model of quantum key distribution. Okay, and the quantity that we're interested in is the non-asymptotic private capacity. So this is the maximum rate of epsilon close secret key that you can achieve using the channel little n times. Okay, so the idea in this formula at the bottom is that you fix the number of channel uses, you fix the quality of the key, this parameter epsilon, it's a number between 0 and 1, and then you're trying to maximize the rate of secret key. I'll talk later what I mean by secret key if there's time, but I think many of you have a sense of what this means. So we're just aiming to make a state that's close in fidelity to an ideal secret key state. Okay, and this is a practical question. Ideally, we'd like to be able to characterize, so that quantity that I described, the double arrows for classical communication, and this quantity P sub n is what I described in the previous slide. So ideally, all right, excellent. Okay, so ideally we'd like to characterize this quantity for all little n and for all epsilon between 0 and 1. And you can interpret answering such a question as giving the fundamental limitations of quantum key distribution. Okay, and at some point, Norbert Lukenhaus interpreted giving bounds on this as establishing benchmarks for quantum repeaters. The idea being that these bounds that you can establish on this quantity are in the absence of quantum repeaters, and you could, as a certificate of having a quantum repeater, say that you can achieve a rate higher than this. Okay, so today I'm going to talk about the tightest known bounds on this on this non-asymptotic private capacity for several channels of practical interest, including the ones that Riccardo talked about on the previous slide. So this is a very brief outline. This is a very brief talk. I'll talk about some examples, and if there's time at the end, I'll talk about the proof idea, and this idea of meta-converse. Okay, so a channel of great practical interest for experimentalists is this photon loss channel. It's described in this way. This is the most succinct description of the channel that you can give in the Heisenberg picture. It's characterized by a single parameter eta, which is the average fraction of photons that make it through from Alice to Bob. And this is the relation between two inputs of a beam splitter and the output of the beam splitter that Bob is able to access. Okay, so what we're claiming in this work is to give a proof. Not only as a consequence of our results, we get a proof for a bound stated in prior work. And so if you take that quantity that I was talking about before, take the limit as n goes to infinity, and then as epsilon goes to 0, you get something that's called in the information theory literature a weak converse bound. And so in the prior work, this bound was presented, and one consequence of our method is a proof of this bound. Okay. So the drawbacks of this are maybe clear, that it's an asymptotic statement, and thus it doesn't say very much for practical protocols that are using the channel a finite number of times. Okay, so what we do in this work for the pure loss channel is we give this refined bound, and this is a non-asymptotic bound that applies for every little n that you could choose and every quality of the key parameter that you could have, every epsilon. And as the first term in the bound, you have that fundamental capacity term, but you also have this term that gets smaller and smaller as n gets larger and larger. So for small n, maybe it's not so tight, but then it gets much tighter as n gets larger and larger. Okay? So that's one consequence of our work. And this can be used to assess the performance of practical quantum repeaters that are using the loss channel a finite number of times. Other variations of the bound are possible. If the transmissivity, maybe in practice, it's not the same for every channel use. So in that case, our methods can apply to give bounds there. Also, if eta is chosen adversarially, then the resulting bound would just be the minimum of all the etas that are available, that are being chosen from. And we do get similar bounds for what's called quantum limited amplifier, and Giacomo talked about that in his work on bosonic entropy inequalities. And this channel, it's appeared quite a bit in the quantum optics literature. It's also relevant for relativistic quantum information theory, if you're interested in more exotic things like the Unruh effect. And we also get bounds for more complex channels called thermalizing channels, more general amplifier channels, and additive noise channels. So in a prior work, this bound was presented for the dephasing channel. So the dephasing channel is one that either the qubit gets through with some probability or a phase flip is applied with the complementary probability. And this is a weak converse bound that was presented. And by combining our proof techniques with prior work of Marco and his colleagues, we can show this expansion of the non-asymptotic private capacity of the dephasing channel. So the first term here is the private capacity, and then the second order term is the backoff from capacity for Finite-n. So if epsilon is less than a half, then this function right here is negative. This is the inverse of the cumulative Gaussian distribution function. So for epsilon less than a half, this is negative, and this term is characterizing the backoff from capacity. And this term here is something called entropy variance, and you can think of it as like the fluctuations about an ideal noiseless channel. And we even have a third order term, which we recover from by connecting with this previous work of Marco. Okay, so to give you an idea of what these bounds can tell you, we have a plot like this. So here on the horizontal is the number of channel uses. On the vertical is the rate. This top line is the asymptotic capacity. So that's what you achieve when n is going to infinity. But what the approaches that we have allow you to get are finer characterizations for a finite number of channel uses. And so we have these upper bounds and these lower bounds, and in between is this third order approximation that I showed you right here. Okay, so briefly about the proof technique. This is something that we call Meta-converse. Well, the name was given by Polyansky and his colleagues in the context of classical information theory. And the idea is to connect to hypothesis testing. So, distinguishing between two quantum states, how well can you do that? This is connecting converses to hypothesis testing is an idea that goes back to the 70s in classical information theory. And it's something that's been explored in the context of quantum information theory more recently by Marco and colleagues. So the fundamental quantity there is something that was given the name hypothesis testing relative entropy. And you can think of it as being like a relative entropy. It obeys a data processing inequality. So it's a function of two states, rho and sigma, and a quality parameter epsilon. And the idea is to minimize the type 2 error of misidentifying sigma subject to a constraint that you identify rho with probability larger than 1 minus epsilon. So that quantity, this quantity on the inside, this is a probability. Take a negative log of that, it's an entropy. Okay. And so as I said, this behaves like relative entropy. If you plug in tensor power states, then it in fact converges to relative entropy. And from such a quantity, we can define an epsilon relative entropy of entanglement. This was actually defined in a work by Nilanjana Datta and Fernando Brandao. So this is a comparison between a bipartite state and the closest separable state in this particular relative entropy distance. And then we can generalize this to be a function of a channel. Okay. So the goal of any protocol is to make a tripartite key state, which looks like this. Alice and Bob at the end would like to share perfectly correlated, uniformly random bits in tensor product with the state of Eve. In a very important work by Karol Horodecki and collaborators, they showed, so this original picture is the tripartite picture of privacy, and they showed how to think about privacy in a bipartite context, and they called this construction a private state. These A and B systems here, up here with the key state, are in correspondence with these A and B systems here. These are called the key systems. These A prime and B prime systems are called shield systems, and this unitary is called the twisting unitary. And so the basic idea is that anyone who has a purification of this state will be in tensor product with the key systems if you trace over the shield systems. That's the basic idea. And so we followed that approach and worked in the bipartite picture. And connecting to prior work, we wrote down this privacy test. So the idea is if you're generating a key, you'd like to test whether what you've actually made at the end is in fact a key. And so the idea is work in the bipartite picture. You first untwist that unitary that was twisting up the correlations for the private state, and then project onto the maximally entangled state. And so that's what this projection is doing. And if the state at the end is in fact an epsilon approximate private state, then the test will succeed with probability larger than 1 minus epsilon. Whereas if you perform this test on a separable state, what Karol Horodecki and his colleagues showed is that the probability of the test succeeding is no larger than 1 over the number of key values. So right here, you have the main parameters encoded in these inequalities, the quality of the key and the rate of the protocol. So by connecting these things and using epsilon relative entropy of entanglement, the fact that it's a comparison to a separable state, this is the statement of the meta-converse that we have, that the non-asymptotic one-shot private capacity is upper bounded by the epsilon relative entropy of entanglement. And then we have ways, this is the basic meta-converse, and then it leads to strong converses and second-order expansions. I think I'm pretty much out of time, and so maybe if you have questions, you can ask me, or if you don't, you can ask some of these. Thank you.
So do we have any questions?
Can you say something more about the third order that bound?
What is it?
You have a third order,
Oh, the third order term for the dephasing channel?
Yes.
So the way this came about is that there are in fact many results. There were results in classical information theory about classical capacity of a bit flip channel and third order expressions that people had identified. And it turns out that the dephasing channel is so simple and has so much symmetry that we can connect to those results. And so that's the rough sense in which this third order term comes about. We don't have a general approach for getting third order terms.
Do we have any other questions? Okay, so if not, just thank Mark again.